Today we're going to be talking about nodal and mesh analysis in the S domain, and I'm going to show you guys how to use MathCAD to make your lives less miserable. So the first circuit that we are going to analyze is this one, where we have a voltage source connected to a 2 ohm resistor. Here we are going to have a 1 Henry inductance. A 0.5 farad capacitance. And here will be a 4 ohm resistor over which we are trying to determine what the voltage Vx of t will be. Across the top here, we are going to have a 6 ohm resistor. And I'm going to short all this stuff down here at the bottom. For our circuit, Vs of t will simply be a 12 volt unit step function. So we're going to analyze this circuit in the frequency domain. Yes. 0.5. I will write that more clearly. Is that more clearly 0.5 now? All right. Okay, so because I know that I'm going to be using MathCAD here in a moment, I don't particularly like to put values in, so I'm going to go ahead and just label all of these components. So I'm going to call this resistor R1, this resistor R2, this is L, this is C, and this resistor here is R3, so that when I write my equations, these are what I'm going to be using. In the S domain, our circuit looks like this. So we are going to have 12 over S volts here. Here is our resistor R2. The impedance of our inductance is just S times L. The impedance of our capacitance is 1 over S times C. Here is our resistance R3, over which we will be finding a voltage Vx of S. And across the top, we have our resistor R1, like so. I am going to use nodal analysis for this particular problem because I only have 2 nodes with unknown voltages. So this voltage is going to be V1 of S. This voltage will be V2 of S, and I'm going to choose to have my bottommost terminal as ground. So we are literally just going to use good old-fashioned nodal analysis here. So when we apply KCL at node 1, we're going to be adding these currents together. So KCL at node 1 looks like V1 of S minus 12 over S divided by R2 plus, so that's the current flowing to the left through resistor R2. The current flowing down through our inductor is going to look like V1 of S divided by SL. And then the current flowing through, flowing to the right through our capacitor is going to look like SC times V1 minus V2. Set this equal to 0. So before we move along from this, does anybody not understand this equation? Hopefully fairly straightforward. The only thing that might be a little odd is that when we divide by 1 over SC, that's the same thing as multiplying by S times C. So effectively what we're doing is just multiplying the conductance of that capacitor by the voltage in order to express the current. All right. Our second equation will come from applying nodal analysis at node 2, or KCL at node 2. So in applying KCL at node 2, we're going to be adding the following currents together. So starting with the current flowing across resistor R1, we are going to have V2 of S minus 12 over S divided by R1. Now the current flowing to the left through the capacitor is going to look like SC times V2 minus V1. And then lastly, we have our current flowing down through resistor R3, which is just going to be V2 divided by R3, and set this equal to 0. So we now have two equation, two unknown systems. And I don't know about you guys, but the thought of solving this system of equations by substitution and elimination absolutely and utterly terrifies me. I am far too lazy to do that. So instead, I'm going to show you how to use MathCAD to do what's called a symbolic solve operation, which is distinctly different from the numerical solve operation that you guys have been doing with your solve blocks in your previous classes that you've had with me. So as soon as this thing catches back up there, all right, we're going to enter this stuff into MathCAD. So I'm going to start with a 2x1 matrix. Okay. I'm going to drop it down here. I'm giving myself enough room up at the top so that I can actually put in my component values later, but we can solve it this way first. And so in this first, let's see, so this would be the first row, I'm going to put in my first expression, right? So that's going to look like, I don't want caps lock on, V1 minus 12 over S divided by R2 plus V1 divided by S times L. I need to make sure that I explicitly multiply here so that it doesn't treat SL as a single variable, because it is not, just to be really clear there. Plus S times C times the difference of V1 minus V2. And control equals to 0. So that's where my first expression goes. My second expression I'm going to type in here V2 minus 12 over S, all divided by R1 plus S times C times V2 minus V1 plus V2 divided by R3 is equal to 0. And now I'm going to go back to the math tab here, and I'm going to go under symbolics. I'm going to press this arrow key. And so what it's doing right now is it's literally just not sure what I'm asking it to do, so it just replicated the results, which gives us nothing remotely useful. If I type in the keyword solve, it's going to think about things here and probably give me an error in a moment. So what I'm going to do specifically here is I'm going to tell it to solve for V1 and V2 symbolically. And it gives me this terrifyingly large thing, which we actually have to expand out. Hold on. Need more space. Do you want to do it by hand? This is way easier. Now I understand that this looks terrifying and you're not wrong. There we go. All right. So this giant fraction right here to the right is V2. And then the giant fraction on the left is V1. While this does look bad, let's see what happens if we go back through here and put in our component values. Right? So I'm just going to scooch this down. So R1 had a value of 6 ohms, and I'm intentionally not using units here. Okay, so this is one of the few times where I'm not going to use units. And because that's just going to make it an even bigger nightmare. R2 was 2 ohms. R3 was 4 ohms. See, every time I give it some new piece of information, it gets slightly less terrifying. L, sorry, was 1 Henry. And C was half a farad, so 0.5. And now we're left with this thing, which is literally just a polynomial in S divided by another polynomial in S. The numerator is of lower order than the denominator, so this is exactly the form that we're looking for. I took the time to figure out what these fractions here are. So for instance here, this 8.727 yada, yada, yada is just 96 over 11. The 5.45 blah, blah, blah is 60 over 11. Let's see, we've got a factor of 17 over 11 in here somewhere. That's the 1.545 in the denominator there. We've got a factor of 10 over 11. That's the 0.909 repeating and all that kind of good stuff. Let's see, I think we also have that 2.18 yada yada, so that's 24 elevenths, which I didn't hit 24. But anyway, we should have all of the different parts of this thing now. So going back to my original sheet here, by using MathCAD, I was able to find that our voltage V1 of S is equal to, sorry, this is going to be a fraction, so let me move this up here. 96 over 11 times S plus 60 over 11 divided by S squared plus 17/11 S plus 10 over 11. And the part that we're actually looking for, since V2 is exactly equal to Vx, we have, 96/11 S squared plus 24/11 S plus 48 over 11 divided by S cubed plus 17/11 S squared plus 10 over 11 S. And like I said a moment ago, this is equal to Vx of S, which is our S domain representation of the voltage that we're trying to find. Okay. So I'm not saying you couldn't get these results by hand, but I am asking why you would ever want to, because it seems like a lot of work. Gabriel. You know, I'm not sure. So if I go into math formatting, which is where I would expect to be able to do all that kind of good stuff, everything's already kind of blacked out, meaning it won't let me select my normal answers. Let's see if I go into text formatting. Nope, that's literally just for text. If I go over here to calculation, calculation options. I don't know what any of those things mean. Yeah, I'm going to stick with my original answer of I don't know. I feel like there should be some way to make it spit out an answer that has fractions in it, but I don't know how to do it. It's worth a Google. Go for it. Yes. Units don't work. I'm not saying that units won't work, but what I am saying is that the units are going to be a little bit wonky. And so what I mean by that specifically, if we look back at our original circuit diagram here, right? So let's talk specifically about the change, right? So here in the time domain, this voltage is very obviously measured in volts. Okay, that is easy peasy to figure out. What are the actual units of this thing, right? So 12 is in volts, but what are the units of S? It's a frequency, so it's actually per second, right? So we would have 12 volts divided by per seconds, giving us volt seconds as our unit. Now, if we look at the arguable impedance of our inductance here, S is measured in per seconds. Our inductance L is in henries, where a henry is a volt second per amp. So that actually does come out to be normal ohms, right? Our resistors are measured in ohms. Our capacitor will wind up also being in ohms. Our currents are going to wind up being in amp seconds because of the way that the units of voltage worked out. And so just because it winds up being confusing, because some things actually have unintentional, let's call it, multiplication by seconds in their units. Other things are going to have division by seconds when we get to that kind of stuff. I find that it's easier to just not worry about the units so much. And then we just need to have an understanding of really putting everything into base units to make sure we're not getting weird stuff out at the end, which was why when I worked the example in class on Friday, I made very sure to call 5 milliamps, 5 times 10 to the minus 3, so that getting out to the end, I knew that my unit was going to be measured in volts, or the units of the voltages or whatever would be in volts. Yes, Daniel.
Obviously, it wouldn't be something this complex. Would we have something like this in the test program?
On the take-home test, absolutely. On the in-class test, not a chance.
Where we have a situation where we have the 0 minus.
Would there be initial conditions?
Yeah.
Absolutely, that's fair game. Yep. And the next circuit that we're going to analyze will specifically have a non-zero initial condition, so that we'll take that into account. And some of your homework problems will also involve non-zero initial conditions as well. So we've used MathCAD to get to this point. Our goal is to figure out what this voltage is in the time domain. So what do we do now? So partial fraction expansion and then the inverse Laplace of that, right? So this is a simple third order polynomial. We can very obviously see that one of our solutions to this is going to be s is equal to 0 because there's a common factor of s. So let the monitor catch back up. This expression here has roots at s is equal to 0, negative 17 over 22, minus j square root of 151 divided by 22. I checked that square root of 151 can't be anything smaller because that's 3 times 67, both of which are prime numbers. So square root of 151 is as good as it's going to get. And then negative 17 over 22 plus j, the square root of 151 over 22. So that means that Vx of s could be written as 96/11 s squared plus 24/11 s plus 48/11 divided by s times s plus 17 over 22 plus j root 151 over 22 times s plus 17 over 22 minus j square root of 151 over 22. Or, using partial fraction expansion, some coefficient a divided by s plus some complex number b. Oh, sorry, I shouldn't have the conjugate there. Over s plus 17 over 22 plus j root 151 over 22 plus b conjugate over s plus 17 over 22 minus j root 151 over 22. Oh. Our coefficient a, once again, is found by multiplying, in this case, Vx of s by s. So that's going to be S times 96 over 11 S squared plus 24 over 11S plus 48 over 11 divided by S times S plus 17 over 22 plus J root 151 over 22 times S plus 17 over 22 minus J root 151 over 22 evaluated at S is equal to negative 17 over 22 minus J root 151 over 22. And this came out to be 24 fifths. Yes. Oh, no, you're absolutely right. That's my mistake. Thank you. Thank you for that. You are absolutely right. So A should be evaluated at 0. Looking at my notes poorly. 24 fifths. Yes. Thank you for that. B is going to be S plus 17 over 22 plus J root 151 over 22. 96 elevenths S squared plus 24 elevenths S plus 48 over 11 divided by S times S plus 17 over 22, J root 151 over 22, S plus 17 over 22 minus J root 151 over 22. This is the one that is evaluated at negative 17/20 minus J root 151 over 22. And here I got 6.300 with an angle of negative 109.819 degrees. And from this, I know that B conjugate is obviously just a conjugate of B, which means I'm going to have inverse Laplace transform for an exponentially decaying cosine function. So Vx of t is going to look like 24 fifths plus 12.599 e to the negative 17 over 22t times the cosine of root 151 over 22t plus 109.819 degrees u of t volts. One thing, I'm not sure, I didn't bring my table that I wrote home. I just brought my textbook home when I was working on this stuff. So one thing I want to make sure, I may have made a mistake when we were writing down the identities for things. But effectively, whatever angle I get here, when I'm finding the root for plus, the sign gets changed here because of trig identities. So because I may have potentially taught it to you incorrectly or whatever, I'm going to fix it on the equation sheet that I'm going to give you guys. With regards to taking points off or getting the sign wrong on the phase angle, I'm not going to worry about that, regardless of whether it's on your homework or your exam, because I don't remember whether or not I taught it to you correctly. I'm not going to penalize you for my mistake. So for the sake of getting it correct, we should flip the angle, but just in case I told you differently previously, I don't want that to be wildly confusing. All right. Questions? nobody's saying much of anything, so let's take a stab at a problem that has initial conditions. So our circuit, the second circuit that we're going to analyze today is this guy. Where we have a 4 ohm resistor, a 24-volt source, an 8 ohm resistor, a 2 Henry inductance through which we're trying to find some current IL of T, 12 ohm resistor. I'm going to have a switch on top, and my switch is closing at T is equal to 0. And then out here on the right hand side, I have a 0.2 farad capacitor. So for T all the way up from negative infinity to 0 minus, this is just a simple DC circuit where we don't need any fancy techniques in order to solve for things, right? So for negative infinity is less than T is less than 0 minus, our circuit looks like this. This short here representing my inductor. Here's my inductor current, IL at 0 minus. Over here is my open circuit representing my capacitor. So this is VC at 0 minus. What value should either of these quantities have? Right, so just 24 volts divided by 24 ohms is 1 amp. Seems reasonable to me. VC at 0 minus would be 12 volts, just 1 amp times 12 ohms. All right. So now that we know what our initial conditions are, for T greater than or equal to 0 plus, the S domain circuit looks like, and then let's do this here. Let me just go up here and label things, because once again, this is the way that I prefer to do it. You don't have to, but when I write my equations, I don't like to put numbers in them. So we're going to have resistor R1 in series with 24 over S volts. So let's talk about this just really quickly. This 24 volts that we have here, or in the time domain, is valid for all points in time because it was a DC source that was always on and we never turned it off. Why am I representing it as if it were a 24 volt times a unit step function here? because we're only interested over the interval for where t is greater than 0. Right? So we don't care what it was doing prior to that. So it's just going to look like 24 volts from t equals 0 and on, which is exactly what a unit step function would represent. My 8 ohm resistor is shorted out because the switch is closed. Now I'm going to have my SL impedance. And I'm going to choose to represent my inductor with the impedance in series with a voltage source. Remember that the current I should be flowing into the negative polarity terminal. The value of this voltage source is just L times I at 0 minus. So in this case, that's just going to be 2. And then down here, we're going to have our resistor R3. Over here to the right, I have the impedance of my capacitor, 1 over SC. And then the voltage drop across here is representing the initial condition. So this is going to look like 12 over S volts. Okay. So first thing, I want to make sure that we are consistent with the S domain equivalent circuits for capacitors and inductors that I've given you guys previously. So have I made any mistakes there about polarities or anything like that? I don't believe I have, but let's just make sure. Everything seems groovy. All right. So because we used nodal analysis for the last problem, let's throw mesh analysis at this one. Also, there are a pretty significant amount of nodes now that we have all of those initial condition voltage sources and all that kind of stuff thrown in here. So mesh analysis is probably also the easier system of equations to write. So this is going to be our mesh current I1 of S. This will be our mesh current I2 of S, and very obviously then IL of S would just be I1 minus I2. So if we apply Kirchhoff's voltage law around mesh 1, we get negative 24 over S plus R1 times I1 of S plus SL times I1 minus I2 minus 2 plus R3 times I1 minus I2 is equal to 0. Writing our KVL equation at mesh 2. We're going to have R3 times I2 minus I1 plus 2 plus SL times I2 minus I1 plus I2 divided by SC plus 12 over S is equal to 0. So here's our equation 1 and equation 2. And once again, while I'm sure we could spend 45 minutes to 3 hours doing substitution, I don't want to, because that's why computers were invented. So switching back over to MathCAD, if I can find my cursor, there we go. And let's just get a new sheet here. Let's throw in our values for things first, right? So R1 was, back here, 4 ohms. R2 was 8 ohms, and while this doesn't show up, I'm just going to put it in there for the sake of argument. R3 was 12. L was 2 henries. C was 0.2 farads. Start with my 2x1 matrix. Know for a fact that that's just going to run into things, so I'm going to move it down here. So we're going to have negative 24 over S plus R1 times I1 plus, let's lump some terms together. So I'm going to have R3 plus S times L. Multiplied by I1 minus I2. Minus 2 is equal to 0. For my second equation, I have R3 plus S times L times I2 minus I1 plus 2 plus I2 divided by S times C plus 12 over S is equal to 0. Outside of this thing, symbolic solve. Let me just show you guys something really quick here. If we only told it to solve for I2, which in this case wouldn't make any sense, but in the previous example, it'll solve it saying, if this thing is true, then this is the solution, which I don't want to bother finding if that thing is true or whatever. So it's probably just the best idea to tell it to solve for everything so that it doesn't have all those weird conditional statements. And we get this result, which is a little prettier than our previous one. Once again, we have a polynomial in S divided by a higher order polynomial in S. So going back to our sheet. We can say that I1 of S was 3S squared plus 77 over 4S plus 15 divided by S cubed plus 29/4 S squared plus 10S I2 was 2S plus 12 divided by S squared plus 29/4. Let me make sure that 2 looks more 2-like. S plus 10. And IL is I1 minus I2. So that's going to look like 3s squared plus 77 over 4s plus 15 divided by s cubed plus 29 fourths s plus 10. Excuse me, s squared plus 10s minus 2s squared plus 12s divided by that same denominator, s cubed plus 29 over 4, s squared plus 10s. So I'm sure 99% of you caught this, but I'm just multiplying this thing by s over s to have a common denominator. So 3s squared minus 2s squared is just s squared. 77 over 4 minus 48 over 4 gives me 29 over 4. And then 15 minus 0 is just 15. And then this is over s cubed plus 29 fourths s squared plus 10s. Okay. This denominator has roots of 0, obviously. And then negative 29 plus the square root of 201, all divided by 8. And then negative 29 minus the square root of 201, all divided by 8. And because it's terrifying to have to type that crap out every time, negative 1.853 and some change, or negative 5.397 and some change is what I'll be basing my calculation. So for this particular circuit, you can see that there are 3 distinct real roots, or 3 distinct real poles. So IL of s can be expressed as s squared plus 29 fourths s plus 15 divided by s times s plus 1.853 times s plus 5.397, or a1 over s plus a2 over s plus 1.853. Penmanship is getting shitty. A3 over s plus 5.97. Because we're running lowish on time, I'm just going to give you the values of A1, A2, and A3, because at this point you should all know how to calculate them. So I have found A1 to be equal to 3/2. A2 was negative 0.761. And A3 came out to be positive 0.261. From this, IL of t was 3/2 minus 0.761 e to the negative 1.853 plus 0.261 e to the negative 5.397 T U of T. All right. Any questions about this? Yes, sir. Right. Okay. So, I don't know why my, oh, I know why my cursor is misbehaving because I'm touching on the screen instead of touching on the trackpad thing. Come on. There we go. Yeah. Wrong direction. So let me get this dumb zoom thing out of the way. So after I make my matrix, I need to make sure I don't want to delete the whole thing or that's going to make everything miserable. So my cursor is on the outside of this matrix. In the math tab, I click on symbolics and then I press this arrow because we are symbolically solving this system. And then I have to explicitly type in solve and tell it what variables I want it to solve for. I guess realistically here, I could have made a third equation that was literally just IL is equal to I1 minus I2 and then have it solve for I3 directly. Didn't try it, didn't even think about it until right now, but the math wasn't that particularly difficult to figure out how to get this minus this anyway, because the denominators are effectively the same. So, anywho, any other questions about this? Yes, sir.
Plus 29 minus 42.
So if there were a positive sign here, no, only going to be conjugates if the inside of this thing is a negative number. So if we're taking the square root of a negative number, that means we're going to have complex conjugate poles. So because using the good old quadratic function from 8th grade math, because this was a positive value, it's just an ugly real number and a second ugly real number. If what's under the radical is negative, then we're going to have a complex number as our thing. All right, anything else about this one? All right, so we're going to burn through something real quick here, and this is actually going to serve as kind of a segue for something that we're going to do in this class later. Not 100% sure if it's going to be the next thing that we're going to do, but it is something that we're going to do. We are going to take a look at the following circuit. And this is an active filter circuit. Okay. To me, this is what the Laplace transform was literally invented for, as far as I'm concerned. Okay. So I have a circuit. Here's my input voltage as a function of time. I'm going to call this a 100 ohm resistor, although honestly, it might be better if we did this without numbers, but it'll be okay. This is another 100 ohm resistor. And then over here, I have an op amp. From this node to ground, I'm going to have a 1 microfarad capacitor. And then feeding back from this node to our output node, I'm going to have another 1 microfarad capacitor. And then the output node of my op amp is where my output voltage is going to be taken. So this is what's called the Sallen key filter topology. And if my memory serves me correctly, which means if people haven't changed things, you guys are going to be asked to implement pretty much this exact circuit, but with different component values as part of your 229 lab at some point during this quarter, if you haven't already been done so. Okay. The most obvious way that this circuit is different than the circuits, the filter circuits that we looked at in circuits 2 is this is an active filter because it contains an op amp, right? So passive filters would not have an op amp or anything like it. It would just be some combination, you know, an RLC circuit or something like that, where we are looking at particular voltage drops across different elements to give us different response. By inspection here, it might be difficult to see what type of filter this particularly is. So what we are going to do is we are going to find what's called the transfer function of this filter, okay? So our transfer function, H of S, is simply the ratio of the output voltage in the S domain divided by the input voltage in the S domain. Just as a heads up, kind of tying things back to what we've done previously, H of T, which is the time domain version of the transfer function, is literally this circuit's impulse response, which means we could convolve it if we were feeling so terrible with any input signal and find out what the output would look like. Or in the frequency domain, we could apply any S domain input signal that is the Laplace transform of our input signal of interest to find out how this signal is going to behave. Right, so we're trying to tie some stuff together and look towards the future. All right. So I want to analyze this thing to figure out what my transfer function is going to be. What do I need to do? Okay, so transforming the circuit into the S domain, obviously the first start. I'm just going to erase some things here. Or actually, I'll just put it in red, right? So let's just call this resistor R. This is going to look like 1 over SC. This is also going to look like 1 over SC. This is going to look like Vn of S. This is going to look like V out of S. Transformed. If we were considering our input signal to be an impulse, that would literally be us applying effectively the number 1 in the S domain to this set. Because the transform of an impulse function is literally the number 1. All right, so now that we have transformed our circuit, what would we do? And how do we analyze it? That's the question. Obviously, we need to analyze it. Okay, so first, yes, we're going to treat this as an ideal op amp, meaning that we know that, because I've already used red, let's use orange here. This current is 0 amps. And this current is 0 amps. Okay. Let's do this in blue. So this voltage, V positive of S, has to be the same thing as this voltage, V negative of S. So now both of our ideal op amp rules have been applied. All right. Okay. So let's call the voltage at this node V1 of S. We're going to apply KCL here. And then we're also going to wind up applying KCL at the second node, right, where the 100 ohm resistor meets, or the rightmost 100 ohm resistor meets this vertically oriented 1 microfarad capacitor. Will we write the KCL equation on our output node? No, we can't because we don't know how much current is leaving the output terminal of the output. So it's not going to give us any useful information. Okay. So if we apply KCL at node 1, we would get V1 of S minus Vn of S divided by R plus SC times V1 minus the out plus V1 minus V2 divided by R is equal to 0. KCL at node 2. We just have V2 minus V1 over R plus SC times V2 is equal to 0. We're trying to get something in terms of V out and V in, and so this first equation has V out and V in and V1 and V2. The second equation has V1, V2, just V1 and V2, right? So what are we missing? Exactly right. We're saying that V2 is equal to V out actually simplifies this thing significantly, right? So we don't need another equation. We've got it down to the number of variables that we need, right? So everywhere we have V2, just replace it with V out. And this one is actually easy enough to where we could do it by hand. I'm not going to, because once again, it's very lazy. But we could have done this one by hand pretty easily here. All right, so let's throw this thing into MathCAD and see what shape it out. Opening up the third new sheet. So R was 100. C is 1 micro, right? So our first equation, we're going to have V1 minus Vn divided by R plus S times, that's not times, C times V1 minus V out plus V1 minus V out divided by R is equal to 0. And our second equation will have V out minus V1 divided by R plus S, sorry, lowercase s times uppercase C times V out is equal to 0. Go back to the math tab, tell it to symbolically solve. So solve for V1 and V out. So doing it this way, I'm telling it to effectively treat the quantity V1, or excuse me, V in as a constant. We can see here, the second expression right here is for V out. So if we want our transfer function, we literally just throw away this v in the numerator and we're done. Right? So we have 100 million divided by s squared plus 20,000 s plus 100 million. What type of filter is this? So when s is very small, what does this look like? A really large number divided by the exact same really large number, which means it passes all of our low frequency signals. As s gets higher and higher and higher, eventually it will be larger than this 100 million. And so we will see that at very high frequencies, our transfer function starts looking more and more like 0. So this is a low pass filter. So looking at this transfer function in the S domain lets us figure out what type of filter we have pretty easily. And it took a lot less work to get the same result that we would have gotten when we were looking at filters by looking at the transfer functions in the omega domain or the regular frequency domain, where we had to explicitly go back and find what the magnitude response looked like and the phase response. Right? So just a different way of looking at it with a little bit more context now. Okay. I think that's enough out of me for today.